Every second, a standard enterprise router must evaluate millions of packets, instantly deciding which traffic routes through to its destination and which traffic is dropped. To manage this massive volume of data, Cisco devices rely on access control lists, or ACLs. These are highly structured lists of rules built entirely on strict permit or deny statements. ACLs generally execute one of two distinct functions. Most often, they act as a packet filter to block or allow specific traffic, but they are also used to identify interesting traffic for advanced features, like determining which data enters a VPN tunnel or a quality of service queue. When used for identification, the ACL isn't acting as a security checkpoint. It behaves purely as a true-false Boolean classification test. A permit statement simply means the traffic matches the criteria for the feature, and a deny statement means it is excluded. Writing an ACL seems straightforward on the surface, but deploying one without breaking a live network requires mastering three separate layers: top-down execution logic, wildcard binary math, and strict topological placement. Without a clear understanding of the underlying math and the router's internal processing engine, blindly typing out syntax from memory guarantees a complete failure of network connectivity. The first critical layer is the logic engine. ACLs are applied to specific router interfaces in a specific direction. Inbound filtering evaluates packets before the router makes any routing decisions. Outbound filtering happens after the routing decision is made, as the packet attempts to leave the interface. Regardless of direction, the router processes every ACL sequentially from the top down. A packet is checked against the first rule. If it doesn't match, it drops to the second rule, and so on, until it triggers a match. The instant a match occurs, the router executes the associated action, either permit or deny. It definitively stops checking. Any rules written beneath that match are completely ignored. This sequential processing creates a strict performance optimization rule for network engineers. You must place the most frequently matched statements at the absolute top of the list to minimize the CPU load on the router. This top-down sequence leads directly to the trap that routinely breaks configurations for junior engineers: the implicit deny. Every single ACL concludes with an invisible deny all statement at the very bottom. You cannot see it in the running configuration, and you cannot delete it. As a direct consequence, if you build an ACL made entirely of explicit deny statements to block specific bad actors, you will accidentally drop all legitimate traffic on the network, because anything that doesn't explicitly match your rules hits that invisible wall at the bottom. Within the Cisco logic engine, all network traffic is guilty until explicitly proven innocent by a permit statement. The second layer is bitwise math. When you specify an IP address in an ACL, you use a wildcard mask. A wildcard mask is not a subnet mask. It is an inverse bitwise matching algorithm used to define exactly how much of an IP address the router needs to care about. Wildcard masks follow a specific binary logic. A 0-bit demands a strict exact match. A 1-bit acts as a don't care variable. Look at this example mask of 0.0.255.255. In binary, the first two octets are all zeros. This forces the router to strictly match the 172.16 portion of the incoming IP address. The final two octets are entirely ones. These are the don't care bits. The router ignores whatever values occupy those host positions. This logic scales to two extreme use cases: matching a single machine or matching the entire internet. To match one specific host, you use the wildcard mask 0.0.0.0. This forces an exact match across all 32 bits of the address. In the Cisco command line interface, you can bypass the math entirely by typing the shortcut keyword host before the IP. The inverse is matching all possible IP addresses. Here, the mask 255.255.255.255 sets all 32 bits to ones, telling the router it doesn't care about any specific numbers. The CLI shortcut for this is the keyword any. By utilizing ones and zeros in this way, wildcard masks decouple your security policy from strict subnet boundaries. Engineers gain granular, surgical control over exactly which IPs the router's logic engine evaluates. The final layer is physical placement. Standard IP access lists, which use numbers ranging from 1 to 99, have a severe limitation. They filter traffic based solely on the source IP address. This diagram maps our network topology. For our scenario, we will treat the left side, router 1 and its connected PCs, as an untrusted 172.18 source network. The servers on the right will be our 172.16 destination network. Because standard ACLs only check where traffic originates, the placement rule mandates they must be positioned as close to the destination as possible. If we violate this rule and place a standard ACL on router 1 to block access to the servers, the router only reads the source IP. It will inadvertently block those PCs from reaching any other network on the internet. The correct placement is applying the standard ACL inbound on router 2's gigabit 0/0 interface. This protects the specific servers while allowing the PCs to route normally everywhere else. Extended IP access lists, numbered 100 to 199, offer vast capability. They filter based on source, destination, protocol type, and specific Layer 4 port numbers. Because they evaluate both source and destination, the placement rule flips. Extended ACLs must be placed as close to the source as possible. The topological reasoning is efficiency. By utilizing a highly precise extended ACL directly at router 1, we drop unwanted traffic immediately. This prevents us from wasting valuable bandwidth, sending doomed packets across the wide area network link. Extended ACLs also introduce port operators. Using the syntax EQ for equals, an engineer can target specific applications. You can permit traffic from a source network, but lock it exclusively to a web server on port 80. Additional operators like GT for greater than, LT for less than, and range allow massive flexibility in carving out exact blocks of allowed or denied services. The technical capability of the list dictates its physical position. Placing the right rule on the wrong network interface triggers widespread and unintended routing failures across the topology. Granular filtering is especially important when handling specific protocols like ICMP. Network administrators often attempt to secure their perimeter with a blanket rule blocking all ICMP traffic from untrusted networks. Blocking all ICMP breaks the network's operational functionality. It drops outgoing ping replies to internal hosts and silences vital routing error messages like destination unreachable. Extended ACLs solve this by targeting specific message types. An engineer can explicitly deny the echo requests used for pings while permitting all other necessary ICMP traffic to keep the network healthy. Beyond filtering user data, ACLs secure the router's control plane. This is achieved using the access class command. Unlike standard lists applied to physical network interfaces, access class applies directly to the router's internal virtual terminal lines. It acts as a dedicated filter for incoming management connections, strictly controlling who is allowed to telnet or SSH into the device itself. ACLs protect the infrastructure's management plane with the same deterministic precision used at the network border. Once the math, logic, and placement are mastered, engineers face one final operational hurdle: the editing constraints of Cisco iOS. Numbered ACLs are extremely rigid. If you add a new permit or deny rule to an existing numbered list, it will stubbornly append to the absolute bottom of the execution order. You cannot delete a single line from a numbered list. One typo means you must delete the entire ACL and recreate the stack from scratch. The modern solution is using named access lists. Named lists allow engineers to assign descriptive context to the rule, improving readability. More importantly, they provide the flexibility to target and delete individual lines without destroying the list. However, caution is still required. Even within named ACLs, newly added lines will still default to the bottom of the execution order, placing them dangerously close to the implicit deny. Cisco access control lists are unforgiving, deterministic filters. Success requires respecting top-down execution logic, writing precise bitwise wildcard masks, and adhering to strict topological placement.